Hello everyone, it's Mr. Spinelli. Today we're going to talk about limits and continuity in the context of algebraic problems. But first we're going to review some of the properties of limits. And so on this one it tells me the limit as x goes to 4 for these three different functions, f, g, and h, are 3, 4, and 7 respectively. So essentially all I'm going to do is just plug those numbers, 3, 4, 7 into these expressions. So I'll do f times g, so the limits for each of those functions multiplied together, and then h minus f over h. So then this just gives me 12 minus 4 over 7. You can combine those. This next one we've got 3 minus g. Well, the limit for g is 4, times the quantity h minus 5. The limit for h is 7. So we should get negative 2 there. This next one, we've got h minus 2g, so h minus 2 times 4, all over f times h is 3 times 7 minus 5 times 4 minus 1. So in this one, we get 7 minus 8, so negative 1 over 0. So this one we cannot compute. We don't have enough information. So not enough info to evaluate. Not enough info to evaluate. Okay, so we'd have to do a technique that we don't yet have in our tool belt. So, and we'd have to have more information to apply that rule. The next one, 4 times f. So we've got 4 times 3 minus 3 times g, and then 2 times h. So in this one we get 0 over 14. 0 in the numerator is fine. So that one's limit does exist, and it's 0. And then on this last one, we've got, you'll notice that the x minus 4 would evaluate to 0, and the x squared minus 16 would also evaluate to 0. So we're going to have to factor that in the denominator. So we've got the limit as x goes to 4 of x plus 4, x minus 4, difference of squares, times h of x. And then the numerator remains exactly the same. So now we're able to remove the x minus 4's because anything divided by itself is 1. So then now we can just plug in numbers. So the limit as x goes to 4 of g of x is 4. The limit as x goes to 4 of x plus 4 is 4 plus 4, which is 8. The limit as x goes to 4 of h of x is 7. So then we simply have 4 over 56. And then I'll let you simplify that. So now another example, different values. F is now going to negative 1, g to negative 5, and h to 3. And we're doing the limit as x goes to negative 3 for all of these problems. First one, we've got a sum. So we've got to do g negative 5 plus h 3, and then cube that result. So that would be negative 2 to the third, which is negative 8. The next one, we've got a square root of a product. So f is negative 1, g is negative 5. So we'd get the square root of 5. It's a good thing that was positive, otherwise we would not have been able to compute it. Then we've got a cube root, 2 times the function f squared, so 2 times negative 1 squared, plus the function g of x, negative 5 squared. And so then we've got the cube root of, that'll end up being 2 plus 25, which is 27. Cube root that, you get 3. This next one, we've got 1 over 3 plus f of x is plus a negative 1 for its limit, minus 3, and then square root f minus g, those limits are negative 1 minus negative 5. So we've got 1/2 minus 3 over the square root of 4, which is conveniently 1/2 minus 3/2, which is negative 2/2, or negative 1. And then this one, we've got a constant function. So the limit as we go, x goes to anything, is just 4. Because remember, if you wanted to picture that, that is simply a line up at 4 that is horizontal and goes forever. So that's just some of the properties of limits that we can exploit to our benefit. And now we're going to look at some building up from direct substitution to all your different techniques. So we're doing the limit as x goes to -1 of this. So first thing you always want to do with limits is see if you can just plug in the number and get a result. -2 times -1 squared. This is a polynomial, so we shouldn't have any issue. So then we've got -4, -2, +7, +5. I'll let you compute that. The next one, limit as x goes to 3. Again, we'll try to just plug it in, direct substitution, so I don't need to rewrite the limit step. I don't have to write limit as x goes to 3 because I'm trying to plug it in to see if it works nicely. So I got 5 minus 6 on top, 9 minus 3 on bottom. There's my answer. Now we got -4. So this one, you notice, on top, it's going to go to 0. And on bottom, the limit will also go to 0. So anytime we see 0 over 0, that doesn't mean the limit doesn't exist. We have to do some algebra to determine what it may exist. Okay, so there's work to be done before you can just say the limit doesn't exist. In fact, 0 over 0 can end up being anything. So then I can say this is the limit as x goes to -4. Notice I have to now write that part again because I'm rewriting the inside, what I'm evaluating the limit of. So I've got 4 minus x, 4 plus x on top in the numerator when I factor. And then on bottom, I'm thinking of factor pairs of -12. So I've got 4 and 3, and I need the 4 to be positive. So I've got x plus 4, x minus 3. And now since these are the same, I can remove each of them. So then I've got the limit as x goes to -4 of 4 minus x over x minus 3. Now if I plug -4 in, 4 minus -4 over -4 minus 3. So on top, I end up adding those. I get 8 over -7. So I get -8/7. So that was drastically different than does not exist. So we've got to do some algebra to make that one look nice and work. This one is another one where the top will evaluate to 0 and the bottom will evaluate to 0 when you compute the limits of numerator and denominator. So I need to do some algebra. So I'm going to take this square root of x minus 3 and the numerator, or sorry, the denominator x minus 9. I'm going to multiply each of those by the conjugate of the numerator. So instead of a -3, I will do a +3. What this will help me do is it'll get rid of that square root in the numerator. And the nice thing is, from difference of squares, when you end up factoring and then multiplying it back together, the square root will be gone in the numerator. So I'm not going to bother multiplying out the bottom because it's just going to be a mess. But on top, square root of x times square root of x is x. My middle terms will cancel, right? You'd have a plus 3 root x and a minus 3 root x, and then eventually the minus 9. But these terms cancel, so you're not going to waste your energy with that when you multiply by a conjugate. But I just wanted to show you that. And then what you see is you have an x minus 9 on top. Oops, I want to use that green pen. So that x minus 9 here, and x minus 9 and that x minus 9 simplify to 1. So I've got the limit as x goes to 9 of 1 over the square root of x plus 3. Now I do direct substitution because it is safe. I will not get 0 over 0. And I get 3 plus 3 in the denominator, so I've got 1/6. Alright, this is another very similar one. The top will approach 0. The bottom will also approach 0. So we've got another indeterminate form of 0 over 0. So what I'm going to do is right away, I'm going to multiply by the conjugate. So 2x plus 22 plus 4, and I'll multiply the numerator by the same thing. So on top, in the numerator, I'm not going to do any work because it's a waste of my energy. So I've got the square root of 2x plus 22 plus 4. On the bottom, the square roots multiply together to just make 2x plus 22. The -4 and the +4 make -16, and all those middle terms will go away. And now if I clean this up, I've got the limit as x goes to -3. Got to rewrite all that top stuff again. And whenever I say the top, I mean the numerator. That's just a mouthful. So 2x plus 22 minus 16 is 2x plus 6. And what you're going to notice is I can rewrite this 2x plus 6. I wanted to erase that. Go away. 2x plus 6 I can write as 2 times the quantity x plus 3. And then I've got x plus 3's that are going to go away. Remember, that was causing me an issue in the top that was evaluating to 0. And now it's gone from both the numerator and the denominator. So I've got equals, and all I have left is this over 2. And I can simply plug in the negative 3. I can do direct substitution. So I've got 2 times negative 3 plus 22, all under the square root, plus 4 over 2. So I got negative 6 plus 22 is 16. Square root that, you get 4. So 4 plus 4 is 8 over 2 is 4. So you notice some of these patterns are repeating. All right, now I've got a piecewise function, which for whatever reason trips people up a lot. And something that's helpful, in my opinion, is to notice that this is splitting up at negative 3 and then again at x equals 4. So sometimes it's very helpful to make a number line. So it's split up at negative 3 and 4. And so what I'm going to do is whenever this is less than negative 3, that means I've got to use this portion. And whenever it is in between negative 3 and 4, I have to use the middle piece. And finally, when it's greater than 4, I have to use this piece. So that's going to help me determine how I evaluate this limit. And so the first one's asking the limit as x goes to negative 4. So negative 4 lives in this region. So I'm really doing the limit as x goes to negative 4, and I use that top piece, that 2x squared plus 3x. And I simply use direct substitution. So 2 times negative 4 squared plus 3 times negative 4. You can do that. The next one, it says x goes to negative 3. Now, the function's value at negative 3, I would use the middle one because I have less than or equal to here. But since it's a limit, I have to actually compute the limit from the left and the right, since negative 3 is one of those places where it's splitting up. So for the limit from the left, I have to do the top piece, the 2x squared plus 3x. For the limit from the from the right, I have to use that middle piece, right? So think of it this way. Negative 3 from the left, I'm using that top purple, dark purple piece. Negative 3 from the right, I'm using that middle green piece. So I'm using x squared. So for the top piece, I've got 2 times negative 3 squared plus 3 times negative 3. I'm actually going to compute this one, so I've got 2 times 9 is 18, minus 9 is 9. And then when I plug negative 3 in and square it, I get 9. I'll show that step. Negative 3 squared equals 9. Since both of these values are the same, then this limit is equal to 9. The two-sided limit is equal to the one-sided limits because the one-sided limits are the same. Now 0, limit as x goes to 0. 0 lives here in the green space, so I've got the limit as x goes to 0 of the x squared. So that's simply 0 squared is 0. 4 is one of those places where it cuts off. So when I go from the left, limit as x goes to 4 from the left of f of x, I have to use the middle piece. Since as I come from 4 from the left, I'm in that green space. So I've got the limit as x goes to 4 from the left of x squared. Simply plug 4 in. I get 16. Repeat all these steps, but now from the right. So x is going to 4 from the right. 4 from the right lives in that light purple space, that pink space, which is 4x minus 1, that bottom piece of the piecewise function. So now I've got 4 times 4 minus 1, which is 15. Since these do not equal each other, this limit as x goes to 4, the two-sided limit, does not exist. And lastly, 6 lives in the pink space. So I'm doing the limit as x goes to 6 of 4x minus 1. which is simply 4 times 6, 24, minus 1 is 23. So whenever I was in one of these cutoff points, right, the -3 and the 4, I had to look at a left and a right-sided limit. They had to be the same in order for the two-sided limit to exist. So now we get into some more fun ones. And if I plug -2 in right away, I notice the top will go to 0, and the bottom, the limit will also go to 0. So this is an indeterminate form. I've got to do something clever. And whenever you see an absolute value, you need to remember that absolute value functions are really piecewise functions disguised. So whenever this inside, this x plus 2, is equal to 0, once you're to the left of that, when you're negative, that inside flips the sign. Sometimes it's easier to look at the definition of the absolute value of x. It's negative x whenever x is less than 0, but otherwise it's just regular old x when x is greater than or equal to 0. So I have the same case up here. I've got it's equal to negative x plus 2 whenever that inside is negative, which is whenever x is less than -2. And then it's plain old x plus 2 whenever x is greater than or equal to -2. Okay, so what does that mean for me? It means I've got to do a left and a right-sided limit. So I've got to do the limit, let's turn that into an L, the limit as x goes to -2 from the left will end up being, from the left means I'm using this piece, okay, and we zipped away. So from the left I'm using that top piece, so I replace the absolute value with negative quantity x plus 2, and it's all over x plus 2, so as you can imagine, it's really the limit as x goes to -2 from the left of just -1, because what I crossed out becomes 1, and so it's just equal to -1. And as you can guess, the limit from the right should be +1, because I'm going to end up using this piece for from the right, limit from the right. So I replace the absolute value with just plain old x plus 2 over x plus 2, which is just 1. Therefore, this limit does not exist because the left and the right-sided limits are not equal. Alright, so now I want to look at the limit as x goes to 4 from the left, right, and then the two-sided limit for this problem. This is one of those really common ones that you're going to see because the bottom is going to evaluate to 0. So this isn't a 0 over 0 situation that can result in anything. Usually what's going to happen here is I'm going to go to positive or negative infinity as I come from the left and the right. So sometimes it helps certain people to make a number line. And if I, to the left of 4, then I want to think about what is this x minus 4 quantity going to evaluate to? And I really just care about whether it's positive or negative. So to the left of 4, so you can think of plugging in a number like 3.999, and if you subtract 4 from that number, you're going to get negative. And from the right, you're going to get positive. And then what's happening is we're then cubing that result. Well, if you cube a negative, it stays negative. If you cube a positive, it stays positive. So then, as I approach from the left, I've got a negative number on top, that -2, and then the bottom is going towards 0. Okay, but it's going towards a -0. So this isn't really correct notation. But what's happening is a negative over a negative is a positive, so this is going to go to positive infinity. And then from the right, you're going to have that negative on top, and then on the right it's positive, so this one's going to go to negative infinity. Since the limits from the left and the right are not the same, this does not exist. Same thing, different function. Now we're going to -2. So you notice the bottom is going to go to 0 and the top will go to 2. So we've got 2 over 0, which is going to indicate some kind of infinity. But now we're working with a quantity squared. So it's x plus 2 squared. So when you're to the left and the right, it doesn't matter because you're going to end up squaring it. So that result will end up being positive. And then the numerator, x plus 4, is also always positive, whether you're just to the left or just to the right of -2. So this one will go to positive infinity. From the right, it will go to positive infinity. And therefore, the two-sided limit is also positive infinity. All right, on this one, we plug 3 in. Direct substitution, top gives us 8, the bottom gives us 0. So what we're really going to write this as is factored. So we've got x plus 5, x plus 3, x minus 3 from difference of squares. So all I really care about is what is the sign of this thing when I'm to the left of 3 and to the right of 3. Now, I'm going to notice that the top is always positive. Okay? The top is always positive, and this x plus 3 term is always positive. So then, as I come from the left of 3, 2.999 for example, and I subtract 3 from it, this part is going to be negative from the left. But then when I do 3 from the right, this part is positive. So what I can determine is that because this was going to go to 8 over 0, if I look at the top, the numerator goes to 8, the denominator goes to 0, I know it's going to be some kind of infinity. From the left, I've got negative infinity. The right, I have positive infinity. Therefore, the limit does not exist. All right, now this is classic. This is called the difference quotient. And what I need to do is actually go through this function, because if I were to plug 0 in right away, this is 0, so then f of x minus f of x, the top goes to 0, the bottom goes to 0. Okay, so off the bat, I know I'm going to have to do some algebra. But what I need to do is I need to replace x with x plus h for this first part. So every single x I replace with x plus h, and I'm going to have to actually cube that. And then from all of this, I have to subtract the original function, and I make sure I put that in parentheses. So x cubed minus 2x squared plus 3x minus 1, and all of this is over h. Now, in an ideal situation, everything that's here, this original f of x, should end up canceling. So let's see if that happens if I properly expand this numerator. So x plus h cubed, that's literally x plus h times x plus h times x plus h, each of those things in parentheses. If you remember your Pascal's triangle, it's going to be equal to this. Okay, so that's all just from doing this x plus h cubed. Now x plus h squared is x squared plus 2xh plus h squared, but then I have to distribute the negative 2. So I've got negative 2x squared minus 4xh minus 2h squared. Then simply just distribute a plus 3x plus 3h. So I've got the 3 distributed minus 1. And now I got to carefully distribute my negative. So I've got minus x cubed plus 2x squared minus 3x plus 1. I can sneak that in there. It's right by the scroll bar. There we go. And that's all over h. So now I notice x cubed cancels with the negative x cubed, negative 2x squared cancels with the positive 2x squared, 3x with the negative 3x, negative 1 with the 1, and just as I thought, all of this stuff ended up going away here, the original f of x being subtracted. So then what I need to do is if I were to plug in 0 now, I notice all of the terms in the numerator have an h in them. So I would end up with 0 over 0 again. So I'm going to factor an h out. So then I've got 3x squared plus 3xh plus h squared minus 4x minus 2h plus 3 all over h. And the reason I do that is now my h's are gone, especially in the denominator. And now I can simply plug 0 in for h. So I've got 3x squared plus 3x times h, which has been evaluated at 0 now, plus 0 squared minus 4x minus 2h is going to 0 plus 3. So then all these terms with h's, once I factor that first h out, anyone that's still got an h left over is gone. And so I get 3x squared minus 4x plus 3. And as we go on, you'll notice that that is the derivative of this original function. We'll talk about what that means later. Same scenario, computing this so-called difference quotient, which is the name of this limit, except for a different function. So now what I'm going to do is replace x again with x plus h. and then subtract my original function. I don't have parentheses, but I'll go ahead and just add them just for emphasis. So I want to do the limit of this, so don't forget, like me, to write the limit as h goes to 0. So if you were to plug 0 in, you would get 0 over 0. So we've got to do some manipulation. So what I'm going to do is I'm going to get common denominators. This is the algebra that many of us struggle with. So I'm going to leave some space, minus 1 over x squared all over h. So I'm going to then pull out my pink pen. Since I've got an x squared in the other term, I need to multiply the first term by x squared over x squared, which is just a fancy 1. And then I've got to multiply the second term after the minus sign by x plus h squared over x plus h squared. Okay, so then I've got the same denominator, and I'm just going to have this minus that. Okay, so I've got limit as h goes to 0 of x squared minus the quantity x plus h all squared over their common denominator, which is the x plus h squared times x squared. And this is still all over h. But if you're good with your fractions, you know this h is really over 1, so then I can put this h, so I can do times 1 over h. So I can really just throw the h down there, and I've got an equivalent statement that is much easier to work with. But again, if I were to plug 0 in for h, I would get 0 over 0, which means I've got to do some more algebra, which in this case means expanding the top. So I've got x squared minus x squared minus 2xh minus h squared. So I distributed that negative in after squaring the x plus h term. And then in the bottom I've still got, I'm going to write h x squared x plus h squared to remind you that multiplication is commutative. I can do it in any order I want. Clean up the top a little bit. My x squared minus x squared is gone. I'm going to factor out an h, which is almost always a step. As far as I know, it always is. I'll look into whether or not it always is. I'm actually going to factor out a negative h, and then I've got 2x plus h in the numerator. In the denominator, I've got h times x squared, x plus h squared. My h's nicely cancel out. I cannot forget that there's still a negative there, though. So I've got negative 2x plus h is now 0. I'm doing direct substitution because it's safe. I will not get 0 over 0. And I end up with a negative 2x on top. And in the denominator, I've got x squared times x, which is x cubed. And that ends up being negative 2 over x squared. And I messed up somewhere. Oh my goodness. What happened, Mr. Spinelli? I should have got negative 2 over x cubed. Where did this magical x come in? This is good. We can all learn together. We can process our errors. Minus x squared minus 2xh minus h squared. This is just what you want in a video. Well, goodness me, Mr. Spinelli. It was x to the fourth in the denominator, right? We had x squared and x squared, which makes x to the fourth. I knew the answer, so I was messing up. So we end up with negative 2 over x cubed. Thank you for watching. There's one more problem. Let's crank this one out. So now we've got a piecewise function, and it's splitting up at negative 3 and at 4. So it wants us to find the values of k and m that will make this function continuous everywhere. Well, I go to those breakpoints of negative 3 and 4, and I want to evaluate the left and right side limits and the value of the function. So I'm going to do the limit as x goes to negative 3 from the left of f of x, which means I'm using that top piece. Again, if you want to make your number line, negative 3 and 4. So for the right of 4, I'm using this part. In between, I'm using the middle. and from the left I'm using the top piece. So from the left I'm using the kx squared minus 2m. Plug in negative 3, I'm going to get 9k minus 2m. Limit from the right, I have to use that middle green space. So that's the x plus 1. So I'm going to get negative 3 plus 1 is negative 2. And then I want to actually compute the function's value at negative 3. And that's where I go to the less than or equal to, so I'm using that green space. So that's going to be negative 2 because I've already computed that. Now all three of these need to be the same. 9k minus 2m, negative 2, and negative 2. So I'm going to set 9k minus 2m equal to negative 2. I'm going to change colors. I'm going to go to x equals 4. So I'm going to compute the limit from the left as x goes to 4 from the left of f of x. From the left I'm using the green space, so that's the x plus 1. So that's going to be equal to 5. And then I'm computing the limit as x goes to 4 from the right, which is that kx minus 3m. And that will be equal to 4k minus 3m. And then finally I compute the function's value at 4. I had looked for that or equal to. So that's that bottom light pink. So that's again going to be 4k minus 3m. And so then all three of these things need to be equal, which means that 4k minus 3m is equal to 5. Now you can solve this as a typical system of equations. I'm going to do it in a way you might not have seen. I'm going to do Kramer's rule. So I replace the 9 and the 4 with the negative 2 and the 5, and I leave the coefficients negative 2 and negative 3 the same. Compute this determinant divided by the determinant of 9, negative 2, 4, negative 3. There are many more efficient ways. I just wanted to show you one. And then for m, I've got replace the negative 2 and the negative 3 with the negative 2 and the 5, and my denominator is the same as the other denominator. It's the coefficient matrix to the left side. So then I've got, in case you haven't seen this, negative 2 times negative 3 is 6, minus 5 times negative 2 is negative 10, so I've got 6 minus a negative 10 is 16. Determinant on the bottom, 9 times negative 3 is negative 27, minus a negative 8, so that'll give me negative 19, and that 19 is prime, so I end up with negative 16/19 for k. And then for m, I do the same thing. I'm going to get negative 19 again in the denominator. And then in the numerator, 9 times 5 is 45, minus a negative 8. So 45 plus 8 gives me 53. So I get that m is equal to negative 53 over 19. Don't believe me? Get Desmos out, plot this function, say that k is equal to negative 16 over 19 and m is equal to negative 53 over 19, and the three pieces will be connected at x equals negative 3 and x equals 4. Thank you for watching this very long video. Have a great day.